the instruments of Voyager 1 have sounded the alarm. After 45 years in space, the ancient probe has suddenly registered a brutal spectacle that has left even the most experienced astronomers open-mouthed, and that has subsequently posed a huge mystery to experts for months. Specifically, it was the most powerful gamma-ray burst of all time, and if you like, the scientists were even confronted with an impossible event here. After all, the outbreak and its afterglow simply did not fit our current models. Today, we will show you exactly what Voyager 1 discovered in space, and why the question marks over the heads of the researchers did not get any smaller, even when they were able to uncover the origin of this mystery. You can be so wrong. When Voyager 1 and 2 plunged into the vast expanse of space on August 20th and September 5th, 1977. Experts predicted that they would last just 5 years, but today we know better, and we know that almost 50 years after their launch, the old probes continue to fly, undeterred through space, and have even ventured into regions that previously represented the great unknown. And that's astounding to say the least. The twin probes, which are identical in construction, were not actually designed to travel into interstellar space at all, but only to gather new insights into the outer planets of the solar system and their moons, which were still largely unexplored at the time, after the first and still partly unique images of Jupiter, Saturn, Uranus, and Neptune were in. NASA decided to extend the mission and have the Voyager probes fly on to the edge of the heliosphere. This is the extended region around the Sun, where the solar wind and its magnetic fields are effective. Since the border region of our home world is not exactly around the corner, it took until 2012 for Voyager 1 to reach the protective magnetic bubble of our host star. 6 years later, its sister probe followed, and it is evident that no other man-made object has ever traveled so far into space. This means that Voyager 1 and 2 have now put 24.91 and 20.84 billion kilometers between themselves and the Sun, which is a huge distance, but one that gives scientists a unique opportunity to study the extreme edge regions of our home system up close and recognize that this wonderful world is actually much stranger than previously thought. Experts have been anxiously awaiting the arrival of the second twin probe to compare the previously gathered information with new measurement data, even though Voyager 1 has been tasked with examining the interaction of the Sun with particles and magnetic fields outside the heliosphere since 2012. At first, the comparison did in fact yield a surprising result, as the researchers had previously assumed that the heliosphere was extended far back and therefore asymmetrical. The Voyager data indicated that we are dealing with a round and therefore symmetrical structure, but the differences were much greater when it came to plasma before entering the helipause, the outermost boundary of the heliosphere. Voyager 1 had registered a strong decay in the plasma currents. The passage into the interstellar medium was again accompanied by strong turbulence in the surrounding plasma, which is why the researchers assumed that we are dealing here with a thick but unstable boundary region. Voyager 2, however, was confronted with something completely different. On the one hand, it only needed half a day to cross the helipause, and on the other hand, it detected neither a plasma lull nor extreme plasma tidal waves. In other words, this time the helipause appeared stable and thin. But how can these differences actually be explained well? Probably with the influence of the Sun, since Voyager 1 encountered the helipause during a minimum in the solar activity cycle. It can be assumed that interstellar magnetic fields and cosmic rays penetrated deeper into the boundary region of the heliosphere at that time. However, the strong phase of activity that characterized Voyager 2's passage may have stabilized the helipause in combination with the strong solar wind. Furthermore, Voyager 2 also confirmed the existence of a structure that had already been predicted on paper. On our side of the helipause, there really is an extended magnetic wall that serves as an additional protective shield against cosmic radiation. In detail, the magnetic field was even stronger than any other in the helipause, and apparently it also has an extremely dynamic character. Experts say that the cosmic barrier is created by magnetic currents that move in the direction of the helipause, where they eventually weaken and flow sideways as soon as the direction of the Sun's magnetic field reverses in the next activity cycle. This process will begin again, but this time with the opposite polarity. It is indisputable that the data from Voyager 1 and 2 have already helped us significantly to shed more light on the mysterious outskirts of the solar system. And yet we must not forget that we are still a long way from having solved all the secrets of the helipause and interstellar space. Although the insight provided by the probes suggests that the boundary of our home world forms a complex system together with the interstellar medium, we are ultimately dealing with a gigantic system here, which so far has only been examined in 2 places. In view of this, experts emphasize how essential follow-up missions are for a more detailed overall picture, but of course these will no longer be completed by the aged Voyager probes, because the full Voyager truth also includes the fact that the cosmic old-timers are now showing signs of weakness, and that the greatest success story in space travel is actually gradually coming to an end. On the one hand, technical complications and sudden loss of contact are now almost the order of the day, and on the other, NASA has been pursuing a strict power-saving plan for some time now, in order to keep the probes operational at all. More specifically, instruments that are not essential for the operation of the spacecraft are gradually being switched off, and in fact, only 3 of the original 10 measuring instruments on each probe are still active. In this way, NASA hopes to extend the life of the Voyager probes into the 2030s. After all, these most distant outposts of humanity continue to provide us with unique data, but the signal that Voyager 1 picked up on October 22, 2017 shows that unique can sometimes also mean elemental and confusing. After all, it registered something that hopelessly eclipsed all previous records. While there are currently 2 strongly contested answers to the GOAT topic involving Lionel Messi and Cristiano Ronaldo, an inconceivable gamma-ray explosion. Voyager 1 was the first to realize that something dramatic must have happened in the depths of space while the probe was racing through interstellar space at its usual speed of about 60,000 km when its instrument suddenly sounded the alarm and reported an inexplicably large influx of high-energy radiation. Voyager 1 thus acted as a harbinger of an unimagined event that was to reach Earth 19 hours later and which surpassed everything comparable many times over in detail. The boat question is resolved all the more quickly because it does not concern the greatest but the brightest of all time, and it obviously does not refer to a football player. Chryson GRB.21098. In addition to filling a whole special edition of the journal Astrophysical Letters, the gamma-ray burst sparked a lot of intriguing questions. After all, what on earth could have caused this unprecedented event to occur? We're talking about a spectacle that had an energy of 18 tera-electron-volts, making it 70 times brighter than any eruption that had ever been seen before. On top of that, the eruption also produced an incredibly odd jet of radiation that pushed the limits of current models of the afterglow of such processes. More specifically, the experts detected a new component in the radio range of the jet for which there was simply no explanation, but other ranges of the spectrum, such as the strong focusing of the jet, also showed confusing anomalies. However, what was responsible for this astronomical record was initially completely unclear at first. The researchers were still discussing the birth of a black hole through the collapse of a massive star or a neutron-star collision, but in the end it would take until April 2024 before they uncovered the true origin of the brutal gamma-ray explosion. However, the James Webb Telescope's analysis revealed that the culprit of this extraordinary event was surprisingly ordinary. It was simply an ordinary supernova, but if this stellar explosion was essentially no different from others, why was it so bright? Well, that is a great question, and astronomers are still only guessing at the answer. The favored theory is that the extreme gamma rays were associated with a special form of explosion when rapidly rotating massive stars collapse. They produce cumulated particle jets that shoot out into space at almost the speed of light, And if these jets are particularly narrow and concentrated, they also produce a particularly bright and energetic beam, and that could well have been the case. With the supernova jet of GRB 221009A, after all, it was one of the narrowest jets ever observed in a gamma-ray burst at the same time. However, astronomers openly admit that other factors could have been involved in the record outbreak, and that it will probably take years before we can explain the cause of the intense radiation, but we can already tell you how you will never again miss a new video from us. Simply press the thumbs up and subscribe to stay up to date with the latest news from now on. We'll see you soon.